but given the circumstances, I have to prepare it as a slide, in a single slide. And I will try to give you the main information about the research we have done in the last month. So the title of my presentation is Multifocal kinoform diffractive lenses based on the aperiodic silver ring sequence. As you probably know, there are many mathematical sequences in the field of mathematics and algebra that can be used in several fields of research. And in particular, we have a brief story with these sequences that are aperiodic, which means that they are not periodic in the sense of a classical period. Aperiodic by a very different kind of periodicity. There are several rules to obtain this kind of sequences. As a brief summary of my presentation, I will present this kind of new type of sequences, which is the silver mean one. And with this,
so can you just come forward so that your voice
okay,
is audible.
Because
Your voice is audible.
You are registered. Okay. So I will present the basic of this kind of sequences, and then I will present two different applications that we have developed. The first one is a new kind of multifocal trap, the multifocal traps, optical traps, in the form of optical tweezers. And the second one is in the form of multifocal intraocular lens. So I will start with could you show this? Okay. So in this part of the slide, I represented the.
Excuse me, sir, you can take this. The pointer. This one.
The point. In this part of the in the first part of the slide, I have represented the sequences, which is probably too small to see properly. But as you see, there are different parts in the sequence that are binary. I mean, they are given by only two single elements, which are represented as A and B. And the sequence is formed by the concatenation of different parts of the two seeds elements of the sequence, which are A and B, and then the next elements in the sequence are given by this operation, which is the concatenation between the two first. So this is repeated several times. In practice, this is an infinite sequence, but it could be truncated at any moment. And we have developed, in this example, up to the number of 4 with the repetitions of the sequence. So, to construct a lens, a diffractive lens with this sequence, we have adopted the following rule. With part of A, there are no phase difference in the lens, and where there is a combination of two different elements, A and B, there is an increasing phase between 0 and 2 pi of the phase of the lens. This is a diffractive lens. So in this part of the slide, you can see the surface profile of the lens, which is a kinoform lens. This is a diffractive lens, which can be converted in a lens with symmetry of revolution around the center of the lens. And as you probably know, when one uses diffractive lenses in practice, we are interested in the focusing properties of the lenses. In the applications that I will present, we have obtained two different interesting properties of these lenses. The first one is that with this kind of phase distributions, the lens is quadrifocal. I mean, the lens has 4 foci located at different axial planes of the lens, and it means that you can focus in light in different focal positions, axial focal positions in front of the lens. As you increase the number of the elements in the sequences, the focusing properties are more well established, where the foci are very thin, and the location of the lens changes. As you probably see here, the scale is in diopters, which is the inverse part of 1 meter, 1 diopter. And we use this unit because we are interested mainly in ophthalmic applications. And in ophthalmic applications, the way you measure the power of a lens, an ophthalmic lens, is in diopters. So, the first thing that I want to remark is that the lens is quadrifocal. And in the first, I need to go up there. Okay? Okay. I need to go up. No, sorry. The image here is okay. And we implemented this lens in an optical prism to trap microparticles, and we have found that with the above mentioned kind of kinoform lens, the main foci of the lens are located in a single part of in a volume of the axial propagation, and these 4 foci are named A, B, C, and D, and these are represented here. Since the foci are displayed along the optical axis, we have tilted the sample in order to see, because if you look this in front, there are one behind the other. And we have tilted the probe to show in this picture different focal points. And you can see here in each focal point there is a single particle trapped. And we have a publication in which, probably with my name in Google Scholar Room, you can find these results in detail, in which we show that these particles are fixed in time, although the medium around them is moving. So these are really optical traps. And this is the first time that an optical trap is shown in different optical trap at different axial positions. So we have a volumetric optical trap. So the quadrifocal properties of the lenses that I'm presenting are have one application, an important application in this area, and the other one is going down now. And the other one is in the form of an intraocular lens. This is another field with different principles, of course, but we are also interested in applications in the ophthalmic area. And I have to introduce which is the main goal of this application. When people get older, the crystalline lens inside the eye becomes many times opacified because of cataracts. And there is the only one solution to remove this problem is to remove the crystalline lens from the eye and put in its place an artificial lens, which is an intraocular lens. Nowadays, there are many kinds of different multifocal intraocular lenses, which can be monofocal, which is probably the most simple solution, because when the eye is operated with a single lens, monofocal lens, the eye is able to see only at a single distances, which are long distances. But if the person needs to read, for example, they have to put glasses to see text or to work with them. But the tendency now is to develop lenses, intraocular lenses that allow people to see at multiple distances. So you need a multifocal lens in the eye. And this is why one of the applications that we have developed is in the form of a multifocal lens. We have shown that with the aperiodic Furlan sequence that I have presented previously, we have the opportunity to design But the transition between one focus and the other focus is very smooth. And this means that a person which is operated with this kind of lenses can see very clearly at distance, very clearly at near distance, and with a relative good visual acuity in the intermediate distance between far and distant. When I mean far, it's from 4 meters and beyond. And when I speak about near distance, I speak about 35, 40 centimeters from here. So in these two positions, the focus is good, and for the intermediate distances, the transition is very smooth. One thing that I have found, and which is relatively known by the ophthalmologists, is that the response of the eye depends on the diameter of the pupil, of the eye. And it means that when we have very big pupils, for example, with very low levels of light intensity, the foci are much well defined, but when the pupil is small, with 3 millimeters, which is normally the pupil that we have with good amount of light, daylight, for example, and in this case, the transition between the two foci is much more smooth than when the pupil is clear. So, in conclusion, we have developed a new kind of diffractive lenses with two very different applications that we have not only suggested but demonstrated in experiments, and we are very proud of this kind of research. So, if you have any questions,
So with this multifocal intraocular lenses will replace the cataract surgery?
no, there are complementary surgeries.
Okay.
Refractive surgery is used many times to correct little defects after the first surgery, which is replacing the crystalline lens by the intraocular. So the calculation of the intraocular lens is not a very precise method, and many times ophthalmologists need to correct little differences between the target and the result, the final result. And this is done by refractive surgery.
So this would be an alternate solution
Yeah.
for the cataract surgery?
So, thank you very much.